this video, we are going to study about allotropes of carbon. So first we need to know what is an allotropy. What is this property? So let's take the definition. Allotropy is a property of some chemical element to exist in two or more different forms. So here we are talking about carbon. So this carbon can exist in two or more different forms. That means they will be chemically same but different physical properties will be there. So consider the example here. Diamond and graphite are allotropes of carbon. They are entirely made up of carbon itself. So how we know that diamond and graphite are made up of pure form of carbon? When we burn carbon and graphite very high temperatures, carbon combines with the atmospheric oxygen to give carbon dioxide. So there will be no residue left behind. This shows that diamond and graphite are entirely made up of carbon and nothing else. I have told you the point that they are chemically same but different physical properties. So diamond is made up of carbon itself, graphite is made up of carbon itself, fullerene is made up of carbon itself, but their physical properties will be different. These are the allotropes. Here the same chemical element is carbon, which exists in very different forms. Now let's study the allotropes of carbon. They exist in crystalline forms and amorphous forms. In the crystalline forms, diamond, graphite, fullerenes, graphene are the examples. In the amorphous form of carbon, coal, charcoal, coke, lamp black and gas carbon are the examples. So here we are going to study about the three important allotropes of carbon. Those are diamond, graphite and fullerenes. We will study in detail about them. Now let's study about the diamond. It is the purest crystalline allotrope of carbon. We know that diamond is in crystalline form. So it is the purest crystalline allotrope of carbon. So now let's look at the structure of diamond. Here each carbon atom is bonded to 4 other carbon atoms. That is tetravalent property. So it is the rigid 3D structure. 3D structure. So look at the each carbon atom. This carbon atom is bonded to other 4 carbon atoms. Here this is entirely made up of carbon and nothing else. Look at this carbon atom. It is also bonded to 4 other carbon atoms. That means it is tetravalent. So here each carbon atom is bonded to 4 other carbon atoms. This property is called as tetravalency. That's why there is no free electron. Why? Because all the electrons are bonded to other carbon electrons. That's why there are no free electrons in the diamond. Now we can say that this diamond is sp3 hybridized. Why? Because there are all single bonds are present. We know that shape of this diamond is tetrahedral. Here it has number of carbons which are linked together tetrahedrali. So tetrahedral means sp3 hybridized and no free electron is present in the diamond. If the carbon is bonded to 4 other atoms and having a single bond, it shows that it is having a sp3 hybridization. And you should remember that diamond exists in the synthetic form and also in the natural form. Synthetic diamonds are always small in size, but the natural diamonds are larger in size compared to the synthetic diamonds. Now comes the question that how can the diamonds be synthesized? So it is synthesized by subjecting the pure carbon to very high temperatures and pressures. When we heat the carbon in the pure form to very high temperatures and very high pressure, then we can synthesize the diamond. And here is the important question that do diamonds conduct electricity and heat? Do diamonds conduct electricity and heat? So now let's answer this question. So you can see in the structure that each carbon atom is bonded with other 4 carbon atoms, and these are the electrons, 4 electrons of a carbon atom. We know that it is a tetravalent. So other 4 carbon atoms are bonded. So there is no free electron present in the diamond. So here is no free electron. If the free electrons are ions present, means they can carry the charge and they can generate electricity. In diamonds, they don't have any free electron. So that's why they cannot conduct electricity. Diamonds do not conduct electricity. The reason is they don't have free electron. No free electron is electrons are present. That's why diamond do not conduct electricity. Do they conduct heat? Yes, they conduct heat. Why? Because they are extremely rigid. Here the interatomic bonds are bonded strongly with each other. That's why this thermal energy is transmitted from one atom to another rapidly. That's why this diamond is a good conductor of heat due to its rigidity of the structure. So the interatomic bonds are tightly bonded to each other. And some important things, let's revise once again. So it is the purest crystalline allotropy of a carbon. Here they are bonded tetrahedrally. And look into the structure of a carbon, that is diamond. Here each carbon atom is bonded to 4 other carbon atoms. That's why no free electron is present. That's why it do not conduct any electricity. But due to its rigidity in the structure, it conducts heat. And it is having sp3 hybridization because of the sigma bonds, single bonds, and tetravalency. And how can the diamond be synthesized? It is by subjecting carbon in the pure form to high temperatures and pressures. These are the important points about diamond. Now let's study about the graphite. So here the graphite is another allotropy of carbon. This graphite occurs in the free state but can also be prepared artificially. Here each carbon is bonded to 3 other carbon atoms. This carbon is bonded to 3 carbon atoms, and this carbon is bonded to other 3 carbon atoms. That is, each carbon is bonded to 3 other carbon atoms, and 1 electron is waiting for bonding. We know that carbon is having 4 electrons around it. That is 1s2, 2s2, 2p2. So in outer valency there are 4 electrons. So 1, 2, 3 are bonded and another 1 electron is not bonded. So here is a free electron present in the graphite. And this free electron is responsible for conducting electricity in the graphite. So if we want to see about the hybridization of the graphite, then it is sp2 hybridized. Why? Because here carbon is bonded to 3 other carbon atoms. That's why it is sp2 hybridized. And it is having a hexagonal geometry. And you can see here these are the hexagons and it is having an hexagonal geometry. And these are smooth and slippery in the nature. Why? Because they are arranged in the form of hexagonal sheets. One sheet is arranged above the another sheet. That's why they are smooth and slippery. So this graphite occurs in the free state in nature, but it can be artificially, can also be synthesized by heating a mixture of sand and coke in electrical furnace at about 3300 Kelvin. That is, it is artificially synthesized by heating a mixture of sand and coke in electrical furnace at about 3300 Kelvin. And these are having van der Waals forces. That is, these are having weak intermolecular forces. Those are called as van der Waals forces. Now we came to know that graphite is a good conductor of electricity. Why? Because of the free electron. But remember that it is a poor conductor of heat. It conducts heat but not much as diamond. Why? Because at high temperatures graphite has an intermolecular structure with immobile ions. Thus this makes the graphite a poor conductor of heat. So as you can see, these are the carbon atoms, hexagonal in shape, and these are the van der Waals forces. These are weak intermolecular forces are present in the graphite, and these are very good conductors of electricity due to one free electron and poor conductor of heat. This is about the graphite. Now we can study about the fullerenes or Buckminster fullerenes, and these are cage-like spheroidal molecules. Look at the picture of Buckminster fullerenes, and why did they got this name? Because it resembles the geodesic dome which is designed by US architect Buckminster Fuller. That's why it has got the name Buckminster fullerenes. That is, it resembles the shape of geodesic dome which is designed by the US architect Buckminster Fuller. Look at the picture of that Buckminster fullerenes which is in the shape of football, and these are having the general formula C2N, where N is greater than or equal to 30. So in the place of N, if we write 30, then we will get C60. This C60 is called as Buckminster fullerenes, which is in the shape of a football, and this is that is C60 is the small fullerenes. Other C540, C70 or other fullerenes. So in the C60 molecule, it resembles a soccer ball with 20 hexagonal faces, 12 pentagonal faces and 60 vertices. Hexagon means 6-faced. That is, look at the picture, you will have a good idea. So here it is a hexagonal face. These hexagonal faces are 20 and the pentagonal faces are 12. So as you can see that these type of shapes are also present in the C60. So these hexagonal faces are 20, pentagonal faces are 12 and 60 vertices. That is, it is having 60 carbon atoms. It is also a crystalline form of a carbon. It is having carbon and nothing else. As you can see in the picture that each carbon is bonded to 3 other carbon atoms. So it is also having sp2 hybridization. So you should know that in carbon only sp, sp2, sp3 hybridization is only possible. Why? Because we can write the electronic configuration, that is 1s2, 2s2, 2p2. So only s and p electrons are present. That's why only these 3 hybridizations are possible in the carbon and allotropes of carbon. Diamond is sp3 hybridized, graphite is sp2 hybridized, and Buckminster fullerenes is also sp2 hybridized. Why? Because it is having 3 sigma bonds. Now let's study about the questions which can be asked in the exam. So now, why graphite is a good conductor of electricity? Why? Because of a free electron. And why diamond is not a good conductor of electricity? Why? Because there is no free electron in the diamond. That's why it is not a good conductor of electricity. And other question is, the graphite was synthesized by? It was Edward G. Aitken. He synthesized the graphite, and the Buckminster fullerenes was discovered by Harry Kroto, Richard Smalley and Robert Karl, and they won the Nobel Prize for the discovery of Buckminster fullerenes. And the allotropy comes from a Greek word. Here allo means other and the tropy means forms. Other forms are nothing but allotropy. And I will say the examples of other allotropes of carbon, that is lensdaleite, C540, C70, single-walled nanotubes or bucket tubes. And remember that C60 is also called as buckyball. So here the diamond, graphite and Buckminster fullerenes are formed of carbon atoms only and nothing else. So we can confirm it by burning them. If we burn them at high temperatures, there will be carbon dioxide which will be released. That is, carbon combines with the atmospheric oxygen to release the carbon dioxide, and there will be no residue which will be left behind. Here these are having same chemical properties but different physical properties in the allotropes. The difference lies in the manner in which the carbon atoms are bonded to one another. This lensdaleite is an important example. They may also ask this in the examination, like whether it is a allotropy of carbon or not. Yes, it is allotropy of a carbon. Thank you for watching.